Jai Hind. In this video, we'll talk about graph traversals. This is in continuation of our previous graph video, in which we talked about graph basics, that a graph is a set of vertices and edges. This we talked about. That then we talked about the ways of representing the graph in terms of matrix or in terms of adjacency list. So if I am having this three vertices graph, then I will have 3 by 3 matrix, and I will enter 1 in ijth location of the matrix if edge exists, otherwise 0. 1 represent the edge between I and j, and 0 represent no edge. Another way is adjacency list, that we store the information about the vertices. My vertices are, let me say, 0, 1, 2, and it's adjacent information in terms of a linked list. Okay, these two, 1 and 2, are adjacent to this, that will be represented in a linked list. So till this we discussed in our last video. Now I'll talk about the traversal, graph traversal. In specific, there are two popular methods of traversal, BFS and DFS. So in particular, we will discuss these two algorithms with example. So now let us start with the introduction to traversal. So what actually traversal is? When I am given a graph G, it means I have a set of vertices and the set of edges, which are pairs of vertices. Now we have to traverse the graph. What does it mean? It means I will start from a point. For example, if we take from a real life, there is a salesman and the headquarter is, let me say, in Ghaziabad only. Then the salesman has to go to each city. So if cities are represented as nodes, so the salesman has to start from one city of Ghaziabad and need to go to all the neighbor city, then next cities, and so on, whatever is the area assigned. Okay, so from a given source node, it has to visit all the nodes. Okay, so which node can be visited? What does it mean when I'm saying traversal of graph starting with a node S? It means visit all nodes in V reachable from S. We can move to that node only which is reachable. Okay, so it means adjacency information we use in graph. Adjacency is very important. We are having vertices and adjacency information, which is actually the set of edges. So we will now discuss about this visiting all the nodes in the vertices set, starting with one specific vertex that we are calling as source node. Okay, so the two methods are BFS and DFS. So we are searching a graph. So what does it mean? We need to follow a system, systematically following the edges of the graph to visit the vertices. Okay, from where we have to follow? From the starting vertex, that is source vertex. Okay, so actually there are so many uses. One is used to discover the structure of the graph. There are two algorithms, BFS, breadth first search, and depth first search. Later we'll come to know that the names are actually given according to the concept used. So two concepts are used. One is you can go breadth wise, and another is you can go depth wise. When you are traversing from a particular point, the traversal can be breadth wise or depth wise. Okay, so now let us discuss the algorithm one by one. Breadth first search, first one. So what we are given? The set of vertices V and set of edges E, and my starting vertex is S. I am starting with S. Breadth first search systematically explores the edges of G to discover every vertex that is reachable from S. As I told, the traversal. It computes the distance from S to all such reachable vertices. It produces breadth first tree with root S. It means it will start from S then it will take its breadth-wise next level and then next level. It produces a breadth-first tree with root S that contains all such reachable vertices. Its name is breadth-first search because it expands the graph between discovered and undiscovered vertices uniformly across the breadth. What does it mean? It means the algorithm discovers all vertices at distance k from S before discovering any vertices at distance k plus 1. That is the concept of breadth. Okay, so now let us understand, try to understand it. Let me say I am having this graph. So if the graph nodes are 1, 2, 3, 4 and this is my S starting node. So if I see this starting node 1, it is at distance 1 from 2. 2, what is the distance from 2? That is 1. Distance from 3, 1. Distance from 4, 2. It is at 2, 4 is at 2 distance from here. So before 4 is discovered or expanded, before that the vertices who are at one lesser distance means 2 and 3 nodes, these will be explored first. Now let us understand it reversively with reverse concept. What is that? This is a node, its immediate neighbors are 2 and 3. So 2 and 3 will be discovered first. Then what is 4? 4 is neighbor of these neighbors. So then 4 will be discovered. Okay, if I expand this as containing 5, then 6. Okay, so now see, 1 will be the source node, then what are neighbors? Means at one distance from here. So breadth wise 2, 3 and 5. These are neighbors of 1. So firstly what will be discovered? 2, 3 and 5. Then what will be discovered? Neighbors of these neighbors. What are neighbors of these? 4 and 6. If I take another node 7. So what will be the scenario? At depth 0, S is there. So from S we will start. At one distance, how many nodes are there? 2, 3, 5. So these will be visited first. What will be discovered first? 2, 3, 5. Now of length 2, distance 2. What are those? 4 and 6. So firstly what will be discovered? 1, then its neighbor 2, 3 and 5. Then these neighbor means two neighbors of 2, 3 and 5. Those are 4 and 6. Then neighbors of 4 and 6, which is only 7. This is breadth first search. Okay, now let us go through the algorithm for this. How do we implement it? This is my one graph I have taken as an example. Okay, so what we will have? We will visit these breadth wise. This is our BFS algorithm. So how do we implement it? We will take a status. Status will actually tell us that we have visited this node or we have not yet visited. Okay, so when status is 1, so how many nodes are there? I have 1, 2, 3, 4, 5, 6 nodes. 1, 2, 3, 4, 5, 6 nodes are there. So everyone is having status 1. The status is 1. What does it mean? It means these nodes have been initialized. These have not yet visited or explored. Okay, there will be some starting node. Okay, then what we have to maintain? We have to maintain the concept, the information about the breadth. Okay, breadth means we will start from a node and then we will consider all its neighbors. That is considered breadth wise. Then we will consider neighbor of those neighbors that we have just taken. So we will implement Q for this purpose. Because whatever we will consider first, we will enter neighbors of that and that will be executed first. Then we will enter the neighbors of those. So it will be first in, first out. So we will implement Q. So we are having repetition of these steps until Q is empty. So what is our concept? Initially all are ready to be executed, to be processed. So let me take some starting node. So let me take 1. 1 is my starting node. So 1 I will put in Q. This is my Q. What I'll put here? 1. In Q I am having 1. So when a vertex is added to Q, its status will be changed to 2. It means it has been taken, it has been considered, and it is to be processed now. Okay. So in processing, what I am taking? In processing, I am taking the display, that the value is displayed. So in Q, I am having 1. Okay. Now BFS is my displaying, processing. So what I'll do? I'll delete one element from Q, remove the vertex n from Q and change its status to 3. So remove 1, deleted from Q, its status has been changed to 3. Let me repeat again. 1 means initial state, 2 means in waiting, it has already been added to Q but not yet processed, 3 means processed. 1 means initial state, 2 means waiting state, 3 means process state. So 1 has been deleted, so it is in process state. The status is changed to 3. Okay, now what is to be done? Examine each neighbor of this. What are neighbors of 1? 2 and 4. So consider each and every neighbor. Okay, so let me consider 2 first. Now if 2's status is 1, it means it is in initial state, nothing has been done. So we will take it to the Q and change the status to 2. Now 2 is in waiting state. What is next neighbor? 4. 4 is 1, yes. Add it to Q. So in Q, 2 and 4 has come. It means what will be processed after 1? Its neighbors. Okay. So now if I see this, both are 1. Now I'll delete one more node, 2. Its status will be 3. It will be added to output. Now we'll see the neighbors of 2. What is neighbor of 2? That is 5. So 5 will be added to Q. 5 is added to Q because its status was 1. Now it will be changed to 2. Okay. So see, firstly 2 has been added and processed. Then its neighbor 5 has been added to the Q. 5 has been added to Q. Now delete next. So we have processed 2 elements, 1 and 2. Now what else we are having? 4. Why we are considering 4? Because it is at the front of the queue. Now 4 will be processed. 4 will be processed means output and its status will become 3. Now what are neighbors of 4? Neighbors of 4 are 2. There is one neighbor 2. Now check status of 2 which is not 1. So we will not do anything. It means its neighbor has already been considered. Okay. Now again delete the front node, that is 5. Its status will be changed to 3. Okay. What is neighbor of 5? That is 4 only. Neighbor of 5? 4 only. So 4 is already processed. So what we found from here, firstly we visited 1, then its neighbors 2 and 4. Then neighbors of 2 and 4, that is 5. Okay. So from 1 we can reach to 5. Firstly we will cover 1, then its neighbor 2, 4, then their neighbor 5. So from 1 these are reachable. This is breadth first search. This is implemented with help of a queue. Now second method is depth first search. What is depth first search? The depth first search strategy, by the name it is clear, it will not go breadth wise like the previous one, it will go depth wise. The strategy followed by depth first search is, as the name implies, to search deeper in the graph. Deeper means we will take a start node, then we will take its neighbors. Now neighbors are to be processed. So in breadth first, what happened? we took first neighbor 2, then we took next neighbor 4. But what will happen in depth first search? After 1, we will take 2. Now 4 is in waiting state, but we will take neighbors of 2 first. We will go on depth. It means one path to maximum depth will be explored first. Okay. In depth first search, edges are explored of the most recently discovered vertex V. Now see the word most recently. It means we need last in first out. Most recently. What is first in first out? Which has arrived first. Now we are saying what is most recently visited. We have to find out neighbors of that. So most recently visited must be on the top. So we will implement, the procedure is same, but we will use the depth exploration. So we will use stack. Most recently discovered vertex V that still has unexplored edges, leaving it. When all of the V's edges have been explored, the search backtracks. Now we will cover those. The search backtracks to explore edges, leaving the vertex from which V was discovered. It means if we took the first, then we visited 2. Now we will go from 2 to another node. Okay, another neighbor of 2, then neighbors, and so on. Once this line is fully explored, then we will take the second neighbor, that is depth wise. Okay, now let us try to understand it. The same graph I have taken as an example. Again, everything is same. What difference I have to maintain? I have to work the last entered node first. I have to process that last entered node first. Okay, so now let me take all the vertices. My vertices are 1, 2, 3, 4, 5, 6. All will have initially status 1. It means all are in initial state. Now what is the difference? We will make a stack. We will use a stack. Now my initial vertex I am taking again as 1. This is my source. Source I am taking as 1. Okay. Now we will put the source on the stack. So 1 is here. Here means it is in waiting state. Now we will pop the last entered node. So this is a stack. So we will pop the element. What we popped? 1. So my DFS is having entry 1. DFS is 1. Okay. So it has been popped. What will be considered? Its neighbors. What are its neighbors? 2 and 4. So those will be pushed onto the stack. What is pushed onto the stack? 2 and 4. Both are neighbors. Both are at distance 1. So you can take any order, 2, 4 or 4, 2. So I have pushed 4 on the stack and then I pushed 2. Any order it can be taken. Now both are pushed onto the stack. It means the status is converted to 2. Why we have pushed it onto the stack? Because both were in initial state, not yet considered. Okay, if these have already been considered, we will not push on the stack. But both were having in the initial state, both has the status 1. That's why we pushed it onto the stack. Now we will pop the element. What we popped? 2. Processed 2. Now what we will do? Its status will be converted to 3. 1 has already been converted to 3. Okay, so what is there? The status of 2 is worked out. Now what are neighbors of 2? 2's neighbor is 5. So it will be pushed onto the stack. When it will be pushed onto the stack, its entry will be 2. Status will become 2. Now again delete the element. Pop the element, process it. What are neighbors of 5 now? That is only 4. Now what is status of 4? Already 2. It means already has been waiting, this is already in waiting state. So nothing is pushed onto the stack. Now pop again, 4 processed. Okay, and what is the state become? 4. Stack is empty, nothing is left on the stack. Okay, so what is the traversal here? We visited 1, then 2, then 5, then 4. So this is the tree for this. 1 to 2, 2 to 5, and 1 to 4. In that case, BFS, what we did? 1, 2, 4, then 5, because 5 was at 2 distance. Here it is at 1 distance. Okay, so that is the difference. In one we we visit the nodes breadth wise, and in one we visit the node depth wise. That is our DFS search. Okay, a little comparison. In BFS, what we do? We visit breadth wise like this. This is our traversal. This is the traversal. First, then total second. In DFS, what is the traversal? We go to one direction, then backtrack, then backtrack. That is our way of processing. In this we go row level wise, in this we go depth wise. Okay, so what is the point to be noted here? If we are visiting here, so it will find the result which is at nearest level, but it may find a solution which is at far distance, because it is going in depth. So as it is moving in depth, so it may reach to a solution which is at distance. It means not the optimal solution, but it may find some distant solution. What else is there? When we are having BFS, in BFS we are maintaining information about all the nodes of next level. Okay, and in this case, what we are maintaining? We are maintaining just in space, we are maintaining in memory just one branch. This branch is maintained after fully executing it. Okay, but in this case, what is there? We are maintaining D also and H also. All the information, because the A has already been explored. So D and E are already on the queue. In this case, H is explored, F and G are already on the queue. But in this case, when we push B on the stack, so A, D, E already has been popped off. Okay, so in this case, only one depth is maintained, and in this case, in DFS only one depth data is maintained, and in BFS the total level. So space complexity here is more. So in this particular video, we talked about traversals of a graph, that is breadth first search traversal, BFS traversal, and depth first, in which we move depth wise. And then we talked about the comparison, that BFS takes more memory in comparison to DFS, but DFS may provide us a solution which is not the optimal one, but it uses comparatively lesser memory. So this is all about our graph traversals. Thank you. Jai Hind.